My name is Michelle. For this slide, I'll briefly explain the fundamental theory used in our project before we move on to the simulation. Let me explain the big difference between Y and delta connections. In a Y or star connection, all three phases are connected to a common point. This creates a four-wire system. Because of the configuration, the phase voltage is lower than the line voltage. The relationship is given by V line equals to square root of 3 V phase. The line current is equal to the phase current. So this makes the Y connection suitable for distribution system, especially when unbalanced load are present. In delta connection, the loads are connected in a closed loop without a neutral point, forming a three-wire system. Here, the phase voltage is equal to the line voltage, and the line current is higher than phase current by I line equals to square root of 3 I phase. Due to the higher current capability, delta connections are commonly used in high power applications. Core difference for this, when comparing both connections, one important difference is the presence of a neutral current. In a wire system, any imbalance in the load causes a return current to flow through the neutral wire. However, delta systems do not have a neutral path. Another difference is power handling. Delta systems are able to handle higher currents at the same line voltage, which is why they are widely used in industrial applications. For power measurement in this project, we applied the 2 wattmeter method to accurately measure the total active power in both Y and delta configurations. In a balanced three-phase system, the phase currents are equal in magnitude and displaced by 120 degrees. By properly connecting 2 wattmeters, we can determine the total active power of the system without measuring each phase individually. Current coil of each wattmeter is connected in series with two of the three line conductors. Meanwhile, the voltage coil of each wattmeter is connected between its line, conductor, and the remaining third line. This method does not require a neutral connection and works for both Y and delta systems. So for a balanced three-phase load, the total active power is calculated by summing the 2 wattmeter readings. The advantages and relevance to this project. The main advantages of the 2 wattmeter method are that it requires fewer instruments, is suitable for high power systems, and can be applied to both Y and delta connections. In our project, this method was used during simulation to measure and verify the total active power, and the results were then compared with theoretical calculation to confirm accuracy.
I am Amina Korea Norman, and my message number is B112410393. So my part, I will explain about unbalanced star circuit, which is WYE circuit. So we can see from this circuit, it is a three-phase circuit with unbalanced load. That we can see from R1 value is 50 ohm and the other value is 100 ohm. We will get the waveform for the unbalanced circuit. The yellow one is for R1 and it can be seen from this waveform, it is show of unbalanced load because the waveform is not same. And from multimeter, it shown all the value of current, power and voltage. So we can see from the current value, we got 4.6 ampere. It is value of R1, which is the yellow one, which is unbalanced load. And the other value is for R2 and R3, which is we got 2.3 ampere for the same load. To clarify the answer, we can make a comparison with the calculation value that will be presented by Umaira. So from this calculation, we can see that the simulation value and calculation value is same. It is a correct one. So this is for I1, I2, and I3. This is the simulation. So we got the waveform correctly and the value also is correct. And this is the wiring that we made in the multi-sim for the star circuit. Why did power change? Balance versus unbalanced. For the unbalanced circuit, it used a lot of power compared to the balanced circuit.
My name is Nur Umaira Farzana binti Nur Rasid and my matrix number is B112410442. So based on what Amina explained about the unbalanced wire circuit, today I will explain about the calculation. So for the unbalanced wire system calculation, first we need to identify the phase voltage, which is VP. As we know, VP is 230 volt, VA is a yellow one, VB is a red one, and VC is a blue one. So VA 230 and angle 0, VB is 230 and angle negative 120, and VC is 230 and angle 120. So next we need to calculate the reactance, which is XL and XC. As we know, we have resistor equals to 100 ohm, inductance equals to 100 millihenry, and capacitor equals to 100 microfarad. So by using the formula, we got XL and XC directly. And then we need to find net reactance, which is X equals to XL minus XC, and we got negative 0.415 ohm. Then we calculate the phase impedance, which is Z equals to R plus JX. So each color we need to find the impedance. So and then ZA for yellow we got 50, ZA for blue we got 100, and ZA for red we got 100 ohm. Next, we need to calculate line currents by using the formula I equals to V over Z. This is from the Ohm's law basically. I equals to V over R. We replace R equals to Z. And then we insert from the formula, and we got IA equals to 4.599 ampere. IB we got 2.3, and IC we got same 2.3 ampere. And then we calculate the neutral current. Neutral current we need to sum up all the IA, IB, IC. And then we got for IN we got 2.3 ampere. We got same as the simulation value. And then lastly we find power for the wire delta, for the wire connection. So by using formula VI cos theta, we insert V, we insert I cos and angle, and we got 1.058 kilowatt.
Hello everyone, my name is Muhammad Abdul and my matric number is B11241066. Today, in this presentation, I will show the simulation of the delta unbalanced circuit. What I'm gonna do is this: present how we make the circuit and explain in short way why it's unbalanced. Second, present the phase and line current, the phase and line voltage as well. Third, I will present the power of the circuit and the wave diagram. So as we can see here, this is our circuit, our delta unbalanced circuit. So the delta circuit is connected like this. The first load connect from the negative of the first load to the positive of the second load. Same thing we're gonna do with the second load, negative from second to the positive of third, and negative from third to the positive of the first load. All these loads are connecting to our voltage supply, which is V1. We choose values as 230 volt for the voltage and 550 hertz. The loads we choose it like RLC circuit. As we can see, all phase are same except R1 we choose it as 50 ohms because this is gonna make our circuit unbalanced. Just change one load in one phase. So the connection here. So I will explain what are these elements. The first one XM2. This one is to show us the line current. I will gonna do one, but I will explain first. First, what we use the two-method wattmeter to find the wattmeter here in the circuit. So the first multimeter is the line current. The second multimeter is the voltage, line voltage, and the third one is the phase current. This one is the voltage, phase voltage, and this one is our oscilloscope. And we have here two wattmeter. So let's press run and let's see. So as we can see now, the multimeter of the phase and the multimeter of the line and the phase. This is the phase, this is the line. So they are different because it's unbalanced circuit that show the values. This is the wattmeter. As you can see, the phase that have lowest load, it has more power. In the diagram, we gonna see our circuit, the third phase, the first phase, the blue one, is the lowest voltage. The second and the third phase, they are same values, so they have same waves.
We have frequency equals to 15 hertz, inductance equals to 100 millihenry, and capacity 100 microfarad. So first, as usual, we find component reactance, which is XL and XC. So we got XC equals to 31.831 ohm. For the angular frequency, we got 314.16, and reactance we got 31.416 minus 31.831. We got negative 0.451 ohm. And then we find the impedance, which is AB, ZAB, ZBC, and ZCA. For each impedance, we got the value 50.00, 100, and 100. And then by using the impedance that we find just now, we can find the current by using Ohm's law, I equals to V over Z. And then for each one, we got current equals to 4.6, 2.3, and 2.3. So this is same as the simulation value. So for line current, IAB minus ICA, and we got 6.078 ampere. Okay, for total power, we determine the phase angle first because we're going to use formula P equals to VI cos theta. So we find the angle for R for resistor equals to 50, we got negative 0.475, and for R equals to 100, we got negative 0.238 angle. And then insert from the formula power equals to VI cos theta, we got for PAB 1057.96 watt, and for PBC and PCA we got same for 5 to 8.99 watt. Lastly, for total power, we just sum up everything, and we got 2115.94 watt.